Significant figures are what allows us to decide how many digits we can report when we're working with scientific measurements. Let's look at an example to understand how this concept works. Suppose you go into the lab and you have to report how many pencils are there in that group. Now, that is a very easy question to answer. We can see that there are 4 pencils. If the question is how long is the red tape, that answer is not that immediate because we can see that the length of the red tape is positioned somewhere between 2.3 and 2.4 centimeters. So which measurement should we report? Based on this example, we can see that there are 2 types of measurements that we can have in science. Exact numbers. They're determined by counting. So it's like the pencils before. We could count and say that there were exactly 4 pencils. So 4 is our defined value. Then there are inexact numbers. These are measured and are measured in any way that is not counting. So our length for the tape was a measurement and it is an inexact number. How do we determine which measurement should we report? In order to decide this, we first have to decide which digits are important in our measurement. So say, for example, that we write a number that has a measurement of 34. In that case, we have all non-zero digits. All non-zero digits are always significant. They're meaningful. If we have zeros, zeros may or may not be significant. Now, if I write a number like 504, that 0, which is in between non-zero digits, will be significant. Reason being that if I eliminate it, then my measurement changes dramatically. If you have zeros to the right, then these are significant if there is a decimal present. So which digits are non-significant? All the zeros to the left of a non-zero digit, and then zeros to the right when you don't have a decimal point. That is actually an ambiguous situation, and the definition depends on which kind of reference system you're using. So let's look at some examples of this. So suppose I have a set of numbers. So I have here my 5013. Now, this contains a 0, but the 0 is in between significant digits. So this 0 is significant. So this will have 1, 2, 3, 4 significant figures. Now, if I look at this number, 21.40, this 0 is to the right. And we said the zeros that follow to the right are significant. So this has 4 significant digits. This number has zeros that precede our number. So these zeros to the left are non-significant. So this number has 2 significant digits. When it comes to this number, 510, then we can see that there is a 0, there is not a decimal point, so this will be a case where it is ambiguous. So I cannot really tell if it's 3 or 2 significant figures. How do I solve that? One way to make sure when you have zeros present in a measurement is to write the number in scientific notation. So if I write this number in scientific notation, I can see that I will write 3.6 times 10 to the negative 2. And that shows me that there are 2 significant figures. Now, if I want to indicate that this is significant, I will write this as 5.10 times 10 to the second. If I want to instead say that this 0 is non-significant, I will write 5.1 times 10 to the second. Now, in this case, I'm telling that there are either 3 or 2 significant figures. Now, when does this concept become important? Suppose I have a paper clip and I want to determine how long this is. Now I can measure this with different tools. So I did print a couple of rulers, and I can see that if I use this ruler, the length of this paper clip is somewhere around between 3 and 4. And if I position it right, I can see that I can guess that it is somewhere around 3.3. I can kind of estimate that, so I can say 3.3, I could say 3.4. Either way, it will be correct because this last digit is what I call the estimate digit. So it's based on my judgment what the value of the digit is. If I want to know exactly what the digit is, I can take a more precise tool. So this one has a division that is on the 0.1. So the previous one had the division of 1 centimeter. So the division is on the unit, and I can estimate one more digit past the division, so past the unit, so I can estimate the decimal. If I use this tool, then I can see that my length is somewhere between 3.3 and 3.4. So I can say that because it's 3.35, for example, I could estimate that. If I think it's in between, I could see it's 3.36 if I think it's closer to the 0.4 mark. So if I have a division on the decimal, then I can estimate one more digit. So I can always estimate one more in terms of position digit than the division. The next question is how to do operations with significant figures. Now, suppose I want to sum up these two measurements, and suppose I measured two different items. One was measuring 3.3 centimeters and the other one was measuring 3.35. If I sum them up, I can see that this will come out to 6.65. So which measurement should I report? Well, the rule is that I need to report the least number of decimals when I sum or subtract numbers. So the least precise measurement is the one that gives me my result. So I would report, in this case, 6.7. Remember that you need to round. You have a 5 here, so you need to round to 6.7. So this will be 6.7 centimeters. What if I wanted to multiply these numbers? Then in this case, I would have 3.3 times 3.35. And these will give me as a result, if I plug it in a calculator, 11.055. And that's my calculator. Now, you can see that this has many more significant figures than either one of these measurements. So I have to determine how many 6 figs I should report. Now in this case, I need to count how many 6 figs I have for each of these numbers that I multiply. So this is 2 6 figs and this is 3 6 figs. My result can only have as many 6 figs as the number with the least number of 6 figs. So this will be rounded to 11 centimeters because it's 11.0, so I will round up to 11. And this is 2 6 figs, which matches the least number of 6 figs. So when you sum and subtract, you look at the decimals. When you multiply or divide, you look at the number of 6 figs. It's two different rules depending on the operation.